In chapter 10.5, we're going to look at two new tests for convergence and divergence of infinite series, the ratio test and the root test. And what we're going to find is that these series are somewhat blunt instruments in that they're going to be inconclusive unless a series converges really quickly or it diverges really, really quickly. But there are quite a few series that are actually quite important that we can describe using these tests. And so the ratio test in particular is going to be very foundational for what we're going to talk about in the next couple of chapters, which involves adding up not numbers, but rather functions. All right, and these two different tests are going to be motivated by the geometric series. And so let's take a look at an example of that. Suppose we've got the series that looks something like r to the n, where an is just r to the n. Notice that if you take the ratio of consecutive terms, so we take term an plus 1, which would just be r to the n plus 1, and we divide that by an, the ratio, and I'll take an absolute value of those. The ratio of those absolute values is going to be, well, that's just absolute value of r to the n plus 1 over absolute value of r to the n. And notice there's one more factor of absolute value of r on top, and so we'll get the absolute value of r. And if that ratio is less than 1, then that suggests that, well, r is less than 1 in absolute value, and so our series converges. So one of the ways about thinking about the ratio r for a geometric series is as dividing the n plus first term by the nth term. And we've showed previously that geometric series that have a ratio less than 1 will necessarily have terms that are getting smaller and smaller and smaller, and they will ultimately converge. All right, so ratios of consecutive terms give us r, but notice we can also think about taking the nth root of those terms. In this case, the nth root of the absolute value of r to the n would be the same thing as taking the nth root of absolute value of r raised to the n, which is just absolute value of r. And so if that nth root is less than 1, then we would conclude the same thing, that we have a convergent geometric series. Now, we can just look at the number r and get to that same conclusion. So computing the ratio and the nth root doesn't really add much in the context of a geometric series. But there are lots of series that don't behave exactly like a geometric series, but they behave approximately like a geometric series. And we can take this idea of looking at the ratio of consecutive terms or the nth root of particular terms and use that to determine whether we have convergence or divergence. All right, so that's the motivation here. Ultimately, what we're going to do is take this intuition that we derive from the geometric series, that both the nth root of the terms and the ratio of consecutive terms being less than 1 is what leads to convergence, and then we'll extend that to series that don't behave exactly like a geometric series, but do so approximately. And the key insight that we'll have is that if I take the limit as n goes to infinity of an plus 1 equal an plus 1 absolute value over an, and say I get some number rho, then what that means is when n is large, so as n goes to infinity, the n plus first term is approximately rho times the nth term. And if every term is just some constant multiple of the previous one, then that means that this behaves like a geometric series. Okay? So with that in mind, by computing the ratio of the terms and taking a limit, we can determine not whether the terms are have exactly a constant ratio, but rather whether the ratio of the terms approaches a constant in the long run. All right, and that brings us to the the ratio test, which says the following. So this is straight from your textbook in chapter 10.5. It says that if this limit exists, so that when you divide the n plus first term by the nth term, and you let n go to infinity, and that ratio, rho, is less than 1, then we can say that the sum converges absolutely. And the idea there is it behaves like a geometric series with r less than 1. If the ratio is greater than 1, then the sum of an diverges, and that's because it behaves like a geometric series with r greater than 1. And if the ratio is equal to 1, then the test is inconclusive, which means the series may converge or diverge. And that's due to the fact that r equals 1 is right on the edge of the two cases. And it can be very difficult to tell. This is only an approximation, right? We're taking the limit as n goes to infinity. That's not exact. That's not saying that the ratio of terms is rho, but rather it approaches rho. And so whether we approach it from or above or below won't affect the limit, but it will affect convergence or divergence. And so rho equals 1 is a boundary case. We need to keep in mind that unlike the geometric series, we cannot tell whether we have convergence or divergence in that case. Okay? So that's the theorem, and the ratio test works in a very similar way. It says, well, even if the individual terms aren't, their nth root isn't exactly a constant ratio, if we can take the limit as n goes to infinity of the nth root of the terms, and we get rho, then we can say that when n is large, that means that the absolute value of an is approximately rho to the n. And so our terms again behave like some sort of geometric series where rho takes the place of our ratio. And again, if we'll go back to our textbook to see the statement of this theorem, it says the following, that if we take the limit of as n goes to infinity of the nth root of the absolute value of an, and we get that limit to be less than 1, then we have absolute convergence. If the ratio or the limit is greater than 1, we have divergence. And if the limit is equal to 1, that the test is inconclusive. And you'll notice those are the exact same three cases as the ratio test. All right, and the reason why they're the same conditions is because the motivation is the same. In both cases, we're looking at comparing our series to a geometric series. And we know if the ratio is less than 1, we have a convergent series when it's a geometric series, and so the same thing is going to be true for a series that behaves like a geometric series. If the ratio is greater than 1, we have a divergent series. And let's be clear, when we say convergent, we mean absolute convergence. And then lastly, for rho equals 1, that's that boundary case where we would have an inconclusive test. Okay? So that's the basics of these two tests. They're relatively easy to apply, although they do require that we take some limits, which are not always trivial to do. And the interpretation is very similar to that of a geometric series, with the only exception being that when we get a ratio or a root that is equal to 1, it's inconclusive in this case, where that was not true for a geometric series. All right, we'll stop there, and in the next video, we'll start some examples where we apply both of these two new tests.